Hello, good morning, class 11. It's very good to see you again. We are discussing the sixth chapter, chemical equilibrium for reversible reactions. And we have covered many topics, and I appreciate the way you guys are doing your work at your home and sending me. Today we will continue the same topic, determination of equilibrium constant, value of equilibrium constant. Yesterday we did it for ethyl acetate equilibrium. Today we will do it for hydrogen iodide equilibrium. Okay, so let me first write the reaction. Hydrogen gas, when reacts with iodine, I2, vapors of iodine, they convert into hydrogen iodide, vapors of hydrogen iodide. Now the hydrogen iodide can decompose back to hydrogen and iodine. So this way, this is a reversible reaction. Okay, and as hydrogen iodide is an important compound and we make it in the industry, we want to learn how to make this reaction go to the forward direction and get more and more hydrogen iodide. All right, to do that, in order to understand controlling the direction of this reaction, we must have the Kc of this reaction. And as I told you yesterday, in future, and of course that future will be today, I will tell you how can we use the value of Kc in order to determine the direction of the reaction. Now, once again, as you all know, we have some moles at the initial state. So we can write number of moles, right? Number of moles at initial state. You can say initial moles, right? So you take known quantity of hydrogen and known quantity of iodine. And in the beginning, there is no hydrogen iodide. As soon as the equilibrium is established, okay, you have, since this is 1 mole of hydrogen with 1 mole of iodine giving 2 moles of hydrogen iodide. So you will give, let us say, 2x, some quantity of the hydrogen iodide. Now this x will be then A minus x and B minus x. If you remember yesterday, there were 2 products, so XX for them, and then we get minus x from A and minus x from B. Here it is a little different. These are number of moles at equilibrium state. Equilibrium state. Now, as you know, we use active masses. So to active mass, we divide by certain volume. So A minus x upon V, B minus x upon V, and it will be 2x upon V. This is the equilibrium concentrations, or you can say concentrations at equilibrium state. Equilibrium state. Now we can write, apply the law of mass action. We can say applying the law of mass action. So what happens? You know, Kc, yeah, we put the product as numerator, which in this case is hydrogen iodide. Since there are 2 Hi, so there is a Hi power 2. And as here you have only H2 and I2. Now we will replace these values by our numerical values. So we will have Kc is equal to 2x upon V whole square, because there is square, divided by A minus x upon V and B minus x upon V. Here V and V square, and there's also V square over there. They will cancel, and you are going to get Kc equals to 4x squared divided by A minus x and B minus x. Just like yesterday, A and B are known quantities. We take them before the chemical reaction. You guys also have made those charts which indicate the value of A and B. The X is the quantity of the HI made at equilibrium state. We can put all the values here. Different reactions, different values, but the averaging value of this chemical reaction is 54. Just like in the ethyl acetate, the equilibrium constant value for that equilibrium was 4. Here it is 54. So that's how you can calculate the value of the equilibrium constant for this reaction. I will now share with you the chart, and it shows the different amount of hydrogen and iodine were taken. This is 1, 2, 3, 4 experiments. Let's say this is the first experiment, okay? Let's say one student, let us suppose Asfand, he took this many hydrogen, this many iodine, and at equilibrium he found that he had this many hydrogen iodide. Second guy, let us just suppose Ayaz Karnani, he took this much quantities of these compounds and he got this amount. And let us say third and four different students took different quantities, they had different values of X. And then when we put these values in our equation, like I have derived, we see the value is 54.3, 54.6, 53.9, 54.1. So it's 54, the average value of equilibrium constant of hydrogen iodide equilibrium is 54, just like it is 4 for the ethyl acetate equilibrium. This is simple and numerical judgment of this thing. We had done it for hydrogen ethyl acetate yesterday. So I'll also bring that one into picture for you. This was our work yesterday. You can see that. Sorry. Okay. This is our work yesterday, where this was A, B, nil, nil. Here is similar A, B, and nil. So then we have XX. So we have A minus X and B minus. Here we have 2HI, so we have 2X. And likewise we do. The rest everything is same, different equations. Here the average is 4, here the average is 54. If there are hundreds of different reversible reactions, they all will have different values of Kc and Y, because it depends upon the reactivity of the reactants and the products. Different reactions have different reactant products, and they have different abilities to react. So the value of X is changed, equation is changed, the value is changed, and hence every reaction has its own value of Kc. Now let's see how practically, there are two sides, the theoretical numerical side of Kc, and other is the side which is called practical side of Kc. How can you find the X? You can find the X by titration against NaOH, and this is a little bit confusing to understand for this, because they are gases. These gases are filled into bulbs, into containers where air cannot go inside, and then we heat those bulbs at 444 degrees C. Okay, now this not in, you can't take in beaker or flask or something, so you need to seal them, close them into a bulb. Now bulb and flask is different. It's a closed container, even air cannot enter, and we heat at this temperature. Now to heat this temperature, it's a very high temperature. So how can you get them? Sulfur, if you boil sulfur, it can be as hot as 440 degrees C. So we need to put this bulb, a closed container containing the two gases, put into sulfur which is boiling, providing enough heat for them to react. So once they react, reaction happens, equilibrium achieved, we open these bulbs in sodium hydroxide solutions. If you guys know indicator, and we can find through titration what amount of hydrogen iodide is present at the time of equilibrium. Here also we use ice to stop, fix, cool the equilibrium so it doesn't move further when we titrate, and then we can find out the value of x or 2x, and we can also subtract from A and B, and we can also find the value of Kc for hydrogen iodide reaction. So you're going to fare the theoretical side, also practical side, and the chart will tell us the average value of Kc for hydrogen iodide equilibrium. So these are two ways, two different topics. They can come in the examination this time because the last year paper I had shown you, it had the law of mass section. So I expect that this time they are going to give the how can you determine the value of Kc for ethyl acetate or for hydrogen iodide. You must remember both, and they're not very difficult and they're actually easy. Now we will do the problems also, but today's next topic is application. Why we need Kc, why we have Kc, all right? Why did we calculate Kc? So it is applications of equilibrium constant, or let's say application of Kc. I repeat again, a manufacturer or a chemist is not interested in reactants. Of course, we have mixed the reactants to get the products, not the reactants. And for reversible reactions in the industry, it's a huge problem. How can we push the reaction towards forward direction and get maximum and quick yield of the products instead of the reactants? So manufacturer or chemist will use the value of Kc or the knowledge of Kc to calculate the direction of reaction. So it is used, number one, to predict the direction of reversible reaction. Right now, you might be wondering how can Kc's value like 4 or 54 help us tell which way the reaction is going. But once I tell you, you all are going to be pretty much convinced. The second is to predict the extent of reaction. Extent of reaction, like how long the reaction will go. Will it stop immediately? Will it reach equilibrium quickly? Or it will reach after some time, okay? This is also important for examination, very much important topic for examination now. First one I will explain, which is how can we predict, or to predict the direction of reaction. All right? This is the first. A manufacturer or chemist will first check which way the reaction is going. If it is going forward, fine. If it's going reverse, then he will do something to make sure it goes forward, okay? And if it is stalled at equilibrium, he will do something to make sure it goes forward. So going forward is our purpose, which we will learn in future. How can we push it forward? But today we will learn how to find the direction of it, okay? So let's suppose we have a model reaction, okay? Well, let's suppose we have a model reaction. Here's A and B form C and D. Just suppose we have m mole of A, n mole of P, giving you x mole of C and y mole of T. Now, the Kc, equilibrium constant from law of mass action, is, as you guys know, is the C power x, D power y, and A power m, and B power n. Now, somehow you have reached the equilibrium and you have found the equilibrium concentration and you have divided, because these are equilibrium concentration, not the initial concentration. And when you divide them, and then you can find out the value of Kc, like we have found 54 and 4 in the previous examples. Suppose, let me just suppose, okay, supposedly, just suppose the value is 10. Okay, now this is, and you're in your factory, you're the boss of your factory, and you know that the product you are making, the value of the equilibrium constant for that product is 10. Now at any stage you check, you add the ice, stop the reaction there, and you divide the concentration at that time of the reactant, of the product, by the reactants. Okay, you do that at any instance. Okay, if at any instance, okay, we calculate the concentrations of C, D, and AB. Okay, and we find that this ratio, the quantity of the products divided by the quantity of reactants, this ratio, let us say, is less than 10. Let us say it's 4. Now, if it's 4, then when the reaction goes towards equilibrium, the ratio equal to 10. Our value is 4. If our value is 4, this is the ratio, product upon reactant. If you want to make it 10, you need to decrease this and increase this. It's a ratio, right? The numerator, denominator, the upper value and the lower value. If the upper value, if this entire ratio has to reach the value of 10, and currently it is less than 10, it is 4 or 2 or 3, then the reactants must continuously decrease and products must continuously increase so that this ratio becomes 10. Did you get me? Like at any instant of your going on reaction, you draw samples of CD and AB and you multiply them active masses and you divide them and the answer is not 10, it is 4. Or let's say it's 5. It is less than the actual value of Kc, which is 10. Obviously, the ratio must reach 10 because when any reversible reaction starts, it goes from initial state to the equilibrium state. So equilibrium state is when the ratio is equal to 10, and right now it is 4. The reaction will continue such that, my dear friends, such that these values continuously decrease. Okay, the one in yellow, and these value continuously increase, which is the one in orange. Only when the yellow will decrease and orange will increase, this ratio will reach 10. Okay, at any stage you calculate the concentration of A, B, C, D and you divide them and you find the answer is less than Kc. Now if the ratio has to reach Kc from 4 to 5, 6, then 7, then 8, then 9, then 10, in this ratio the denominator must decrease and the numerator must increase, which means the reaction will continue to go in a forward direction. Reaction proceeds in forward direction. I hope you've understood this. If not, then case 2 and case 3 will increase your chances of understanding this. Let's say case 2. Okay. At any instance, you went in there and you draw the samples and you divide the ratio. Okay. If at any stage of your reaction, you do this, you find the amount of product at that time and the amount of reactants at that time. And you are surprised to see that the ratio didn't come 10, it came 15 or 14 or more than the value of Kc. Now this is alarming situation for you. This must worry you as hell, as a manufacturer, as the owner of a company which is making a product. If the ratio of product upon reactant at that time is more than Kc, it means that to reach equilibrium, all reversible reactions try to reach equilibrium, they must decrease this ratio to 10. Decrease is also only possible if the products decrease and reactant increase, but that will be a reverse reaction. All right? This will be a reverse reaction, which means that it is going in a reverse direction. So what will you wish for? You will wish that at any stage of your reaction, the ratio of the products upon reactant should always be less than the value of Kc. And that you can only do if you know the Kc. So in the first place, knowledge of knowing how to find Kc is more important. Because if you know Kc, you can see whether the reaction is going in a forward direction or a reverse direction. The third question which might appear in your mind is, what if we divide these product upon reactant and our answers is 10, exactly as Kc? If at any stage you divide the products upon reactants and the ratio is equal to Kc, comes as 10 as a standard value of Kc for this reaction, should you be happy that your reaction is going forward, or should you be happy that it is going back? Should you be happy that it's going forward, or you should worry that it's going reverse? Okay, tell me. Of course not happy, because you want forward reaction. And if at any stage the product upon return equals the same as the value of the reaction, which is 10, your reaction has come to a stop, my friend. You're getting products and reactant both at same rate. Do you want it? No. As a manufacturer, we do not want to get reactants. Which case will make you happy? Of course, case 1. As long as the ratio of product upon reactant is less than Kc, the reaction tries to reach Kc, and in doing so, it consumes reactant and produces products. That is what we want here. So I always make a small joke in my classes. And if you're an improver listening to this lecture, or a class 12 student this lecture, you might remember it. Okay, suppose you have 3 chemists. You have a factory where you have 3 chemists working at 3 different reversible reactions. Okay, as a boss, you go there and your chemist A. Okay, the chemist A, and when you just take out the product and return at this time and you divide them, the ratio becomes equal to the Kc of that reaction. For a chemist B, it is more than the value of that Kc for that reaction. And for the chemist C, the ratio is less than the value of Kc. Now, which chemist is giving you profit? Is it the first chemist, the chemist A, which is in which the reaction ratio is equal to Kc? Of course not. He is not giving you any profit, because he has put the reaction to stop. You should better fire this chemist and hire a new one, because he couldn't make sure that it should go in a forward reaction. He put the reaction at equilibrium. Okay, not going forward, not going backward. And if chemist 2, if his ratio is more than the given value of Kc for that reaction, suppose he's doing esterification and his answer is not 54, sorry, not 4, but his answer is 15. This is the guy, okay? You should not just fire him, but you should put him to jail because he's giving you a lot of loss. His reaction is going backward. You're not getting any product, you're at loss. And what about the third chemist? Let's say he's making the hydrogen iodide for you. And out of 54, at that time when you checked, the answer was 23. So the ratio was less than the Kc. And you're very happy because this reaction is going in a forward direction. And you're getting more products than the reactants. So I hope you understood that if we know the value of Kc, we can tell whether it's going forward or backward or equilibrium. Now see, you can also cram. Cramming is also there, possibility that the product upon rated, if it is less than Kc, it's forward, more than Kc is reverse, and equal to Kc, equilibrium. But you must understand that if the ratio is equal to Kc, reaction has already reached equilibrium, it is not going anywhere, okay? If it is less than the value of Kc, reaction wants to reach Kc, and to reach equilibrium, it must destroy the denominator and increase numerator. Decrease in reactant, increase in product. That's a forward direction, my friend. So this is our preferable condition. If the ratio is more than the Kc, then to reach the equilibrium, the products must consume to make more reactants. That's a reverse reaction. We don't want that. I hope you have understood how can we use the value of Kc to determine the direction of. So far we are not controlling the direction, but we are predicting that where it is going. Is it going forward or backward or if you didn't know about the 54 or 4 or 10 or the value of Kc, how could you predict the direction? So Kc at this stage is helping us predict the direction of the reaction. Okay. The next application, the extent. Extent, how far the reaction can go. Will it make a lot of products for you, or can it naturally make you more products, or can it make you naturally less products? So the case 2 is to predict the extent of reaction. Extent, limit. Here again, we have 3 cases. Case 1 and case 2, and let's say case 3. Now, let me introduce you some model reaction and their, let's say the conversion of ozone, O3, into oxygen. Okay. This is ozone, converts to oxygen. Now at room temperature, the value of Kc for this reaction is 10 power 55. Is it a big value of Kc? Really, a huge value of Kc. Kc is equal to product upon reactant. Now, if you have a very large value of Kc, it means at equilibrium, there's a lot of O2 and a very little O3. Correct? Your reactant is unstable. It's chemically unstable and it is getting destroyed very easily. You get a lot of product. So, and as a chemist, as an industrialist, you will definitely want to choose those reactions in which the Kc is large. A larger Kc shows that equilibrium, you always get more numerator and less denominator. Okay, let me take another example to give you some surprise. Suppose you took this reaction and you want to prepare fluorine from this. Okay. The Kc for this is 10 power minus 13. That's not good for you because it means that at equilibrium stage, the product is almost so much less. The ratio is equal to 10 power minus 13. Now, when will this come? When this guy is a lot and this guy is absolutely not. Minus 13 value of Kc. It means that the reactant is very stable and it doesn't break down to give fluorine. It shows that reactant is stable. Will you use this kind of reaction in your industry? No. Who wants a reactant which doesn't react? And how do you know? You will ask a reactant, hey reactant, will you react or not? No, he won't answer you. Then how would you know if he is capable to react or not? The value of Kc will tell you. Yeah. If you ask HF, hey Mr. HF, will you decompose easily? Okay. Will he reply to you, yes boss, I will? Of course not. He can't speak. But if you check the Kc value in a chart and if it is too low, like minus 13, it indicates that equilibrium, you have a lot of HF and absolutely very little fluorine. So this is not your choice. On the other side, if you see in the chart, the Kc is like, if you are a manufacturer and you want to make product and you have 5 to 6 options to choose from, which reaction will you choose to make that product? Of course, the reaction with the largest value of Kc. It has the largest extent. Larger the value of Kc, larger will be the extent of reaction. All right. Now, let me show you another one. Nitrogen plus hydrogen from ammonia. The Kc of this is 10. Now, Kc is like 10 or Kc is like 54 or Kc is like 4 are moderate. What? What is this? Moderate, like not too much stable products, not too much stable reactants. All right? We as a chemist prefer these reactions which are moderate because we can switch at our will, them go in one direction or the other direction. Okay? This is moderate value of Kc. This is high value of Kc. High value of Kc, high extent. More products, almost less reactants. Very low value of Kc, right? It means no products but more reactants. If you know about fractions, something upon something, right? In that case, if you have a ratio too big, it means the numerator is more, products are more, and if the value is too small, it means denominator is more, so you have more reactants. And if it is moderate, it means the quantities are moderate. This is the large extent. This reaction is a very large limit. It's a very small extent. And this is a moderate extent. So my dear friends, this is how you can predict the extent of a chemical reaction, and this is how you can predict the direction of chemical reaction, and this is how you can find the value of Kc. So if you don't find the value of Kc, how can you be predicting direction? How could you be predicting the extent? So calculating the value of Kc is the most important step. All right. I hope you have got this lecture very clearly. You can ask me any questions if you have. Now I must announce a test for Friday. Friday, first class will give a written test. And topics are chemical equilibrium, law of mass action, deriving the value of Kc, Kp-Kc relationship, and these topics all topics we have learned in this chapter. This test will be happening at your home. You will make a test copy and in your parents' supervision. Okay, now it's up to you. You want to cheat or not? It's your future. So learn these topics. Make a small copy. Give your copy and book to your parents, your elder brother, sister, cousin, father, grandfather, grandmother, mother, and give the test on a page. And then I will be very happy to see their remarks on your copy. Do share with me. The first theoretical part of this chapter is over, which is understanding the reversible reaction, equilibrium, Kc, and all this. Next part will begin from tomorrow, and that part is controlling, like how can you move it from left to right or from right to left. That will start from tomorrow. And then once we finish that, we will go to do the problems of the sixth chapter. So don't try a problem now unless I reach the stage of problems. I want you to fare these, I want you to remember these, I want you to give the test, and once you are very, very strong in these topics, then I will take you towards the problem sections. So guys, prepare yourself for the Friday's test, and I hope you will do good. Thank you so much. With this, we will end our class. See you tomorrow, same place, same time. Goodbye.